In this section, we're going to cover turning on the oscilloscope and acquiring a single trace on the oscilloscope. So what you see up there on top is a signal generator. That's going to work as our test device. It could be any type of medical device. And I've already got it set to a 1 kilohertz signal that we know we should be measuring. But let's go ahead and set up our controls on the oscilloscope before we turn it on. So go ahead and follow along with the video and go to the vertical mode and set that to channel 1. And what I plan to do was actually mess up the controls and do this along with you. So there we go to channel 1. Set the channel 1 AC ground DC toggle switch to ground. And so we're going to put that to ground right there. Select auto triggering, meaning the hold off is pushed in and the hold off button. So this is pushed in. Make sure that's all the way in. Set the trigger coupling to AC. So if it wasn't, we'd move that to the AC mode. Set the triggering source to channel 1. And according, if that wasn't set to channel 1, we'd set that to channel 1. Set the all position controls and intensity controls centered. So, I'm sorry, set all position controls centered, meaning put everything to the center, except for the main here. The hold off right about there. And position, intensity, focus, and there we go. And set the main time-based control to 1 millisecond per division. This is the main time control, remember? So we're going to change that to, hopefully you can see that on the video. And here we're actually ready to turn on the power. So the power button is right here, and we will get a signal on there. Now, as you can see, the signal on the graticule here is off center. So what we're going to do is go ahead and adjust that to 0. Okay. Now the next part, we're actually going to go ahead and acquire a single trace. So here we see that you have a trace on the CRT. We can also adjust the brightness and the intensity if it's too blurry. So if it wasn't strong enough, you could actually increase the intensity. We do it this way. See that? That's good. If it was out of focus, if it was too fuzzy, we could actually increase or change the focus, so you can actually get a sharp line there. Let's go ahead and change that position right to 0. Okay. So after we've done this, let's go ahead and connect a probe to the input jack. And so this is a probe. Show you the whole thing. Right here. We're going to connect it to channel 1. And it's a BNC connector. You just got to find out where the grooves are, push that in, and then lock it into place. Okay. Now connect the channel 1, ground to the chassis of the device. Now for our demonstration here, this is going to act as our device, and I'm actually outputting the signal to through this cord. And so I'm just going to go ahead and connect ground to ground. Now this is the ground for the oscilloscope probe. So we're going to connect those together. All right. And the next thing is we're going to go ahead and connect the probe tip to the signal. This could actually be some point on a circuit board, but for our case, we're going to connect it right here. Make sure I get that on there, connect. Okay. All right. As you can see, it doesn't look like we have much on the waveform. So the next thing we want to do, since we're getting an AC signal, move the channel 1 AC ground DC switch out of the ground position, because remember, the ground actually blocks both of them, sets AC and DC to ground. And we need to set this to AC. And there we go. Now we can position the waveform vertically as we desire, so we can go ahead and make this center above the 0 coordinate on the y-axis. Let's go ahead and increase the magnification, or the volts per division, excuse me, on the waveform so we can get a better look at it. Right there. And we do have a waveform that should be steady, but it seems to be fluctuating, and this could just be because of feedback, because I have the wires actually overlapping. We probably have an electromagnetic field that's causing some induced EMF on the probe tip. So let me just lay these out. And so that induced EMF is actually causing resistance and causing that waveform to actually decrease. It's actually a really good example of how EMF on inductors cause resistance. There we go. So now I can change the magnification, and there we have a single trace on our oscilloscope. Now if it was unsynchronized, meaning, see if I can get this to unsynchronize. Meaning the waveform wasn't steady. It was actually moving. It would look like it's moving across. You could actually synchronize the waveform to trigger on a certain voltage, and then you would get a steady input the way we do here. But I've got a very good output signal for my signal generator. I'm capturing it really well here on my oscilloscope, and the Gradical here shows that I have a little over 2.5 divisions at 0.1 volt per division. So what you could do is multiply 0.1 times 2. Let's say it's 2.5. We just kind of move the decimal point over, so this would actually be about 0.25 volts per division, 0.25 volts peak to peak. Thank you very much, and we'll go to the next video on dual trace. So in this section, we're going to talk about collecting a dual trace on the oscilloscope. As you can see, I have two signal generators up here, one at 1 kilohertz, or it's about 997 hertz, which is close enough to 1 kilohertz. On the top one, we have 10 kilohertz, or just slightly over. You can see there on the Gradical that we have two waveforms, the slower one being the 1 kilohertz, a longer wavelength, and the one with the shorter wavelength at 10 kilohertz. And in order for us to view this, we need to have the vertical mode to dual. If I turn this to channel 1, I'm only going to be viewing the channel 1 signal. If I'm on 2, again, I'm looking at that 10 kilohertz signal. If I go to dual, I'll actually be looking at both waveforms simultaneously. The other thing we need to have set are right here, we need the AC coupling on both channels. And what we want to also have is set this to on the source to alternate, meaning it's going to be alternating between channel 1 and channel 2. And so this is not actually simultaneously. We're actually looking at two signals being represented on the Gradical at a very, very fast rate. Okay, what else do we need to know about this? So we can actually adjust the position of the signal if we want to look at each one and not overlapping. So I can kind of do something like this and adjust each signal independently. All right. Now by doing that, I've actually changed the trigger a little bit. Okay. I'm going to show you something really cool. We did talk about mathematics on the waveform. Oops, let's do this again. Right there, right there. Okay. Alrighty. So if you want to actually do some addition of the waveform, we can just hit the select switch down here to addition, and what we're going to see is addition of both signals together. And so it would look something like this. Let's go ahead and re-trigger that so you can see how that looks. Kind of cool, right? So what we have here is the 10 kilohertz waveform riding on the 1 kilohertz waveform. Now let's say we wanted to subtract that. If we wanted to subtract that, remember what we do here is we actually change the negative slope, and it doesn't actually make a difference. All right, dang it. Now let's continue with a couple of more operations here on these two waveforms. So with the setup the way it is, we're actually in alternate mode, meaning that the trigger source is either signal. So in this case, we're going to see these two signals as if they're both happening at the same time. But let's say you have one signal that doesn't actually occur until the previous signal occurs. So for example, let's say the 10 kilohertz signal won't actually be seen until it gets triggered by the first signal, the 1 kilohertz waveform. And we're not going to see it on this one because I'm actually having both signals being generated by our signal generators independently, and so neither one is being triggered by the other. But if I had it on channel 1, it's not going to look different here. All I'm saying is that channel 2 can't happen until channel 1 is met, the condition for channel 1 being met. So when we meet that threshold for whatever channel 1 is. And so in a signal like this, you wouldn't see but one channel being operated. And just the same thing for channel 2. We would not see channel 1 unless the condition for channel 2 was triggered, whatever that voltage trigger is for channel 2. So in this case, we would actually just see one signal being channel 2, and until it hit that threshold for whatever activated channel 1 to be looked at on the screen, we would then see that. Now, it's not to say that these signals aren't actually occurring simultaneously on a circuit board, or in this case, the function generator, but say you're looking at a very specific operation of a circuit board and you're looking to see what happens at an initial state when something happens like this, then in that case, you would want to capture that particular signal. Okay, now in the previous demonstration I showed you about adding signals. If we wanted to actually subtract signals, we could actually invert the waveforms. And so we do this, remember when we talk about the negative and positive slope. When it's pushed in, we have a positive slope. Now look at the waveform, it's actually going to invert and we get a negative slope. Now when I do add, it's not going to look much different because these waveforms are moving kind of fast. I can do this and then probably try to trigger the focus real quick. Oh no, it actually does look different. This is good. So this is what it would look like, a subtraction of the one signal from the other, subtracting the 10 kilohertz from the 5 kilohertz by basically making one signal negative. Nice. Okay, so in this next part of the training video, we're going to talk about Lissajous images. And we do that by setting the oscilloscope into the XY mode, which you'll see right up here. And what we need to do also is switch the vertical mode to XY right there. So what that ends up doing is sets up channel 2 as our Y-axis and channel 1 would be our X-axis. So here we're looking at amplitude over amplitude. What I've also done is I've changed the frequency for the first signal to 1 kilohertz and the second one to about 1 kilohertz as well, so you can kind of see everything in one particular graticule. If I increase the amplitude of one of those drastically, it'll leave the screen. So that's the amplitude, and then the frequency. Let me show you what that looks like. Yeah. Because it's happening too fast in one of the axes. So in this case, channel 2 is right up here on the top one, and so the Y-axis is actually oscillating much faster. But if I put them both together at very close frequencies, we're going to see a Lissajous figure that's like this. And we use this to sort of compare both frequency amplitudes together simultaneously. And I can also change the amplitude to match. Right there you can tell that it looks rectangular, where it's shorter on the horizontal axis, and if you look at the vertical axis, meaning channel 2, it's actually a little higher. Let me go ahead and see if I can lower that. There you go. And right there. So we can kind of take a quick look looking at a Lissajous image to get some quick information about both waveforms. And that concludes our training for the oscilloscope, BK2190B.